Welcome back to Enhance, the Environmental Health Analysis Curriculum and Experience. Today, we are on part 2 of our Environmental Health Sciences crash course, Health Effects and Environmental Agents. We will be looking at 4 case studies that cover the health effects and associations of 4 different environmental agents. Although there are many facets of environmental health, today we will focus on 4 primary areas: air, water, soil, and consumer products. Each of these areas will have an associated peer-reviewed paper. So let's jump right in. Let's look at air first in Dr. Helen Powell's Ambient Coarse Particulate Matter in Hospital Admissions in a Medicare Cohort Air Pollution Study, 1999 to 2010. Translation: stuff in the air and its relationship with hospitalizations in a subset of the Medicare population. There are a few key terms we should be aware of before we move on. Though Medicare Cohort Air Pollution Study sounds like it's part of the title of the paper, it's actually the name of a dataset. This is a billing claims administrative health dataset for Medicare enrollees. The dataset includes demographic variables like age, race, ethnicity, a rough location, and medically related variables like the primary diagnosis upon admission into the hospital. This is the first example of an administrative health dataset which we'll see pop up frequently in the environmental health sciences research. These datasets typically provide us with a health outcome variable of interest, like the number of asthma-related hospitalizations or the number of cardiovascular disease cases. These case numbers allow us to quantify 2 very important concepts in epidemiology: mortality and morbidity. Mortality is typically expressed as a rate of the number of people who die due to a particular disease in a given population over a set period of time. Morbidity is another word for illness and is typically also quantified as a rate of a particular disease in a given population. There are a lot of diseases out there. For insurance companies to bill for the treatment associated with certain diseases, there needs to be a coding system to classify and confirm diagnosis. Enter the International Classification of Diseases, or the ICD-10. The 10 refers to which version they're on. They update it every so often to add new diseases and to refine the diagnoses of old ones. An example of this coding system is J45, which denotes asthma. Researchers can make use of this medical coding and administrative datasets to research environmental health topics. Now let's look at a few environmental key terms we'll keep hearing about throughout this course. If you spend any time in this field, you will certainly hear the terms PM10 and PM2.5. PM stands for particulate matter, and the number refers to the size. Particulate matter refers to solid or liquid particles in the air that are typically too small to be seen with the naked eye. But if you've ever seen those little floaty bits in the ray of sunlight, you're actually seeing some lovely little particulate matter. Here we can see a comparison of different particulate matter sizes compared to a human hair, which is about 50 to 70 micrometers, also called microns, in diameter. For perspective, there are 25,000 microns in an inch. The lump in the bottom here, that's a grain of beach sand, about 90 microns. The little blue spheres that can fit comfortably on the human hair, that's the larger particulate matter PM10, which is particulate matter with a diameter less than or equal to 10 microns and includes things like combustion from gasoline and wood burning, dust, and pollen. This also includes indoor particulates from things like cooking, sweeping, even candles. See those pink little spheres on PM10? That's PM2.5, which includes any particulate less than or equal to 2.5 microns. And yes, technically 2.5 is included in PM10. This size of particulate comes from many of the same sources as PM10, but the even smaller size means it's even easier to inhale these particles even deeper into the lungs. For example, PM10 may be caught in and irritate the nose and the mouth, PM5 in the airways, PM2.5 in the lungs, and PM1 even deeper into the lungs. Not good. Particulate matter can irritate airways and exacerbate conditions like asthma and even cause certain lung diseases. So it makes sense to look into the role that exposures to PM play in health-related outcomes. As a quick side note, in this series we'll sometimes refer to something as an exposure to mean a substance, contaminant, or a pollutant that is in the environment for the person to be exposed to. Now that we're acquainted with a few key terms, let's look at the first study. One of the first questions you should ask yourself when reading a paper is, what is the main goal or objective? What research question are they trying to answer? Take a moment to try to answer this before we move forward. The main goal of this study was to estimate the associations between PM10 and PM2.5 exposure with emergency hospitalizations related to cardiovascular and respiratory diseases. What would you hypothesize? Do you think different sizes of particulate matter would have different effects on these outcomes? Would more PM increase the number of emergency hospitalizations? Let's find out. As a budding researcher, the methods section will become more and more important to you. Full disclosure, I used to skip a lot of the methodology when I was an undergrad, but now it's one of the most important parts that I look forward to reading and scrutinizing. Take the time to try to read through the methods. It's worth it. This study examined the time period between January 1999 to December 2010 and included 110 counties in the United States where there were more than 20,000 Medicare enrollees that were at least 65 years old. To assess the exposures of interest, PM 2.5 and PM 10, the author used the EPA's Population-Oriented Air Quality Network, which measures atmospheric pollutants. The concentration of PM 2.5 and PM 10 were recorded from different monitoring sites for a minimum of 200 days to calculate a county-wide exposure estimate. To assess health outcomes, the total number of people being hospitalized for cardiovascular or respiratory illness was tallied over a total population of interest. Cardiovascular outcomes include things like heart failure and stroke, while respiratory outcomes include respiratory tract infections and chronic obstructive pulmonary disease, or COPD. All right, so now we have some measures of exposure and the outcome variables. Now what? Take a deep breath, hopefully without too much particulate matter. We're going to move into some statistical key terms, but it's gonna be okay. The goal of this study was to estimate the associations between PM and health outcomes. This is done by performing a linear regression, specifically a Poisson regression. A linear regression basically tries to predict an outcome based on some explanatory variable. We want to see how much something goes up or down for some unit increase in the other variable. Remember geometry? That slope thing with the rise over the run? Yeah, it's actually really applicable. Have a look here. Our explanatory variable on the x-axis is the number of environmental health science videos you watch. We suspect that the number of videos you watch will explain the outcome variable, your environmental health sciences knowledge. How much does your environmental health science knowledge go up for every video that you watch? In this made-up example, every video increases your knowledge by about 9.6 points based on the linear regression analysis. In this paper, the linear regression is trying to predict the total number of hospitalizations, the outcome, based on some explanatory variable, here, exposure to PM. We want to know how much hospitalizations go up or down for some unit increase in the exposure of interest. The Poisson part means this linear model is for count data. From this model, we derive a single point estimate for the exposure. This just means we estimate one number for the relationship between exposure, the PM, and the outcome, hospitalization. In our environmental health sciences video and environmental health sciences knowledge example, for every video you watch, your knowledge goes up by 9.6 points. 9.6 is that 1 point estimate. However, all statistical methods have uncertainty associated with them, so it's good to present results with their corresponding interval, like a confidence interval, which can roughly be thought of as a range of results you'd expect to see if you repeated the study many times. So instead you could say for every video you watch, your knowledge increases somewhere between 7.8 and 11.4 points. Notice how 9.6 is right in the middle. In this study, they report a posterior interval, sometimes called a credible interval, which can for the most part be interpreted as the confidence interval, though it comes from a different class of statistics known as Bayesian statistics, but you don't need to know about all that for right now. Lastly, there's lag. Lag refers to the literal lag between the exposure and the health effect. For example, say you're exposed to something today, but it takes a few days to manifest as a health outcome. Those few days are the lag. Now that we've got our stats terms, let's have a look at the results. They report a few different things, which I encourage you to look through yourself. But for now, we're going to focus on figure 2. So what's going on here? Let's first look at the axes to orient ourselves. On the x-axis, we see that for a 10 microgram per cubic meter exposure increase, meaning if we were to increase the amount of PM by 10 micrograms per cubic meter, which relates to basically inhaling more PM in every breath, this is the expected percent change in the total number of hospitalizations. On the y-axis on the left, we see the lag, which tells us what, if any, differences we see in health effects over different lag periods. Then we have what are known as facets. That allows you to put even more variables into a plot. Here we can see the percent change in the outcome for different PM sizes and for different health outcomes, the cardiovascular and the respiratory. We can see that for cardiovascular disease, for a 10 microgram per cubic meter increase in PM10, including 2.5, and PM10 adjusted, excluding PM2.5, there is roughly a 0.6% increase in hospitalizations, which may not seem like much, but recall that there were about 6.4 million hospitalizations to begin with. A 0.6% increase equates roughly to another 40,000 cases. That is another 40,000 people in the hospital. And this is just looking at the older population. The point represents the point estimate. Here, 0.6%, and the bar around it represents the interval, or the range that the true point estimate could be. For PM2.5, the interval, though it's hard to see, it crosses 0, which means a 0% increase is a possible value. This means the results are not statistically significant, which suggests that there may not be an association. For respiratory diseases, we see that only PM2.5 appears to have a statistically significant association, also about 0.6% increase. In figure 4 of the paper, they show the specific increases for each disease outcome, which I encourage you to have a look at. But the take-home message is summed up here. Higher PM concentrations are associated with an increased number of hospitalizations for cardiovascular and respiratory illnesses. Air pollution and its associations with health have become a hot area of research in the field as new exposure analysis techniques are developed and rich air pollution data from local and national monitoring systems are easier to access. All right, enough about the air. Let's dive into water. What is the most recent water crisis that comes to mind? Is it Flint, Michigan? Well, you're in luck because that is what our next article is about. Elevated blood lead levels in children associated with the Flint drinking water crisis, a spatial analysis of risk and public health response by Dr. Mona Hanna-Attisha. In 2014, the Flint, Michigan water source was changed from a Detroit supplier to the Flint River temporarily while they were building a new pipeline. Soon after, residents noticed the water looked, smelled, and tasted weird. E. coli was detected in the water, as well as other types of bacteria. To correct this, they added some disinfectants to the water. Now, bacteria is certainly bad, but things got a lot worse when the lead got involved. The water from Detroit was not as corrosive as water from the Flint River. The higher level of corrosiveness resulted in lead leaching out of the lead plumbing into the drinking water. Fun fact, plumbing comes from the Latin word plumbum, meaning lead. As we briefly discussed in the first video, lead can have a slew of negative side effects, but the most alarming are the neurological effects, especially in developing children, which can affect intelligence, behavior, and overall life achievement. It should also be noted that though this particular article focuses on water, this case study also exemplifies issues regarding environmental justice. Many of the individuals burdened by, in this case, lead exposure, are impoverished and/or people of color. This increased burden is a long-standing issue that goes back decades and can be linked to structural racism like historical redlining and racial covenants. That being said, let's get back into the water. The goal of this study was to estimate the blood lead levels in children before and after exposure, that is, the switch in water source. They also used a Geographic Information System, also known as GIS, which is this awesome framework that enables researchers to take spatial aspects into account and perform spatial statistics, which are near and dear to my spatial stats heart. They wanted to determine which areas in Flint were most affected to prioritize the public health response. They also compared Flint to nearby cities. They included children under the age of 5 who had blood lead levels measurements before the water source change. There were about 700 Flint and 1,000 outside Flint kiddos. In addition to the blood lead levels, they also had demographic and geographic information on the participants. They classified children as having elevated blood lead levels if they had a blood lead level of 5 micrograms per deciliter or higher. They also classified different wards in the city as high or low water lead level, with 15 parts per billion or greater as the cutoff for high. They also did this fancy spatial technique called ordinary kriging with spherical semi-variogram model. But don't worry about the specifics of that. Because they only had data on a handful of children, they used this fancy spatial statistics technique to fill in areas of the map where they have no measurement. We'll have a look at the map in a bit, but first, let's look at Figure 1. Figure 1 shows a bar graph that illustrates the differences in lead levels pre and post water source change. The little asterisk denotes that the results were statistically significant. The authors found a statistically significant increase in the percent of children with elevated blood levels from 2.4% to 4.9%, roughly double. And in the areas classified as high water lead level, the percent of children with elevated blood lead levels went from 4% to 10.6%. Now let's have a look at the map. The map they created shows clustering of elevated blood lead levels within the city limits, as expected, shown here in the darker color. These higher lead level areas correspond with the exposure in these areas. That is, the areas where children had higher blood lead levels are the areas with high water lead levels. These areas also correspond to, surprise, areas where the residents are most impoverished. Other exposed but more affluent areas may have been less affected because they took preemptive measures such as changing where they source their water by preemptively switching to bottled water, for example. The authors also looked into alternative sources of lead exposure and found none. This is important because you can imagine certain city officials may want to minimize or deflect blame in such an environmental health emergency. After a press release shared some preliminary results of this study, Michigan's governor reported that 3 schools in Flint had water lead levels in the toxic range, and 1 school had nearly 7 times the level that the EPA would consider actionable. The results from this paper, especially the map, provided the city with guidance to be able to best target interventions like blood screening and bottled water or filter distribution. This is a great example of environmental health research in action. All right, let's get out of the water and dig into some soil. In recent years, some people have taken to growing some of their own food in their backyard. In urban areas where residents do not always have their own soil, community gardens have become more prevalent. Wonderful, right? Well, there are a few things to consider with urban agriculture. In a study by Dr. Lupolt titled The Safe Urban Harvest Study, a community-driven cross-sectional assessment of metals in soil, irrigation water, and produce from urban farms and gardens in Baltimore, Maryland. They looked at 104 urban agricultural sites in the city of Baltimore. Specifically, they measured the concentrations of the following non-essential metals: arsenic, barium, cadmium, chromium, lead, nickel, and 3 essential metals: copper, manganese, and zinc in the soil, irrigation water, and the grown produce itself. Their objective was to compare the concentrations of these metals to public health guidelines for soil and water. Surprisingly, there are no public health guidelines for the metals in produce, so the authors compared the results from the produce grown in urban gardens to the produce from farmers markets and grocery store produce, which included conventionally grown and organically grown farming methods. The authors found that the concentrations for all metals were at or below the public health guidelines for the irrigation water and the soil. Unfortunately, there were some statistically significant differences between the metal levels in the produce from urban gardens versus the grocery produce. However, there was no consistent pattern, and we really don't know what these results mean in isolation. More research is needed. Now you might be thinking, well, that doesn't sound very interesting or conclusive. And honestly, that's really more what science looks like. We think that science is a bunch of eureka moments. But in reality, it's more like, I wonder what this means. This is a good example of an article that highlights how little we know sometimes. There are no set guidelines for these things because, well, urban gardening is kind of a new thing. Maybe you'll be the researcher to develop these guidelines in the future. But if you want to dig into something juicier, go have a look at the soil research that looks into the effects of insecticides and herbicides. All right, we've covered earth, air, water, and now fire. No, wait. Well, wildfires are also an issue, but for now we're going to look at consumer products and chemicals. For our final paper in this lesson, let's look at Dr. Leslie Quiros Alcala's paper, Exposure to Bisphenol and Asthma Morbidity Among Low-Income Urban Children with Asthma. First off, what on earth is bisphenol? Maybe in recent years you've seen water bottles or plastic containers advertising BPA free. Well, they're referring to bisphenol A specifically. BPA is a chemical used in the production of certain plastics, used a lot in food storage containers, water bottles, canned food liners, and various baby products like baby bottles and toys. BPA can leach out of plastic products, which is why you might have heard to not reuse plastic water bottles, especially if the plastic is heated, say in a hot car. The authors were interested in the association between pediatric asthma and BPAs, as well as their cousins, BPS and BPFs, which were developed as a replacement chemical for BPA starting around 2010. To investigate, for 1 year, they followed a sample of 148 mostly low-income African American children between the ages of 5 and 17 years old with asthma. To quantify the exposure of interest, they collected urine samples to measure the amount of BPA and friends in the samples, which are excreted in the urine. This is an example of a biomarker of exposure. That is, you can measure something in the air, water, or soil, or you can also measure it in a biospecimen. The outcome variables of interest were asthma symptoms expressed as the number of days in the last 2 weeks with asthma symptoms like coughing, wheezing, or tightness in the chest. Other outcome measures included lung functioning measures and healthcare utilization, meaning how often they had to go to a healthcare facility for services related to their asthma. They reported the results as odd ratios. Odds ratios are a measure of association between an exposure, BPA, and an outcome. For example, they found that for a 10-fold increase in BPA concentrations, the odds ratio for experiencing asthma-related symptoms in a given day was 1.40. This means there is an estimated 40% increase in the odds of experiencing a day with asthma-related symptoms in the past 2 weeks for every 10-fold increase in BPA. If an odds ratio is less than 1, say 0.75, this would suggest there is a 25% reduction in the outcome of interest. And what's with that tenfold increase bit? This is a common way to express odds ratios, by expressing them as a unit increase. For a unit increase of an exposure, here tenfold, or in a fancy math speak, a log 10 transform, what is the effect or the association on the outcome? For the number of asthma-related emergency department visits, the odds ratio was 2.12. Meaning there was a 112% increase in the odds of having an asthma-related emergency department visit for a tenfold increase in BPA concentrations in the urine. Curiously, they also found a difference in the association between boys and girls. In figure 2 of their paper, we can see the point estimate of the odds ratios and the corresponding interval for various asthma-related symptoms. The black dot represents males and the white diamond represents females. If the odds ratio crosses 1, this means the results are not statistically significant and suggests there may not be an association between the exposure and the outcome. Notice how none of the specific outcomes for females had a statistically significant odds ratio. However, 3 of the 7 outcomes were significant for boys, namely the general symptoms, nocturnal symptoms, for example, how often they woke up at night due to their asthma, and the maximum number of days experiencing symptoms. Though it is beyond the scope of this paper to explain exactly why this is, they suggest it could be related to the fact that BPA is a xenoestrogen. It sounds fancy, but xeno just means foreign. So literally, BPA acts like a foreign estrogen in the body. This could have stronger associations in males due to the differences in the sex hormone composition between males and females. Though this sex difference was not the primary interest in the study, it highlights the importance of stratifying analysis. That is, analyzing people in different groups, like by sex. Otherwise, important differences may be missed and could exacerbate disparities. Check out the sex differences that have been found in heart disease for a good example of why it's important to look at groups separately too. Woof! What a journey that was. But this was just skimming the surface and was only meant to give you a quick introduction to some of the research in the field. I highly encourage you to have a closer look at the papers we reviewed here. What questions did this research spark? Which did you find most interesting? Keep those in mind as we move on to the next parts of this course, which is exposure assessments. We've got to be able to measure exposures to be able to assess their effects on health. Ask yourself, what kind of environmental exposures do you think are worth measuring? How would you go about measuring them? Would you just measure the amount of some exposure once or over time? How do you summarize those results? All good questions that we will dive into in our next lesson. I will see you then, my young budding researchers. Cheers.